What if reality isn't made of matter or energy at its deepest level, but information? Could the universe itself be performing a grand computation? Across physics, computer science, and philosophy, a growing number of ideas suggest that reality itself might be fundamentally computational. While it can certainly verge on science fiction, it isn't all crackpottery. From black holes to quantum mechanics, from entropy to simulation theory, serious thinkers have argued that bits, logic, and information may underlie the laws of physics themselves. Here, I'll provide a taxonomy that organizes the main concepts that explore this idea, sorted into 3 categories. Accepted physics, ideas derived from mainstream empirically supported theories, proposals for new physics, speculative or emerging hypotheses that extend known physics, analogies and interpretations, conceptual frameworks and thought experiments. Each concept offers a lens through which to view the universe as a kind of information processor. Accepted physics. These are ideas derived from or within well-supported theories and principles from mainstream physics that incorporate or imply a deep connection between information and the physical world. Holographic principle. The information that fits inside a region of space appears to be limited not by its volume, but by its surface area. Black hole studies uncovered this twist. A black hole seems to store everything that falls in on its event horizon. Taken seriously, that hints that our 3D universe might be a projection of 2D data written on a distant boundary. Black hole information paradox. If stuff disappears into a black hole, is its information gone forever? Quantum theory says information can't just vanish, yet naive calculations say a black hole destroys it. This tension has driven decades of work and ultimately inspired the holographic principle, suggesting the data survives, may be smeared over the horizon or encoded in Hawking radiation. Quantum error correction. Built to keep qubits stable in quantum computers, error-correcting codes now turn up in quantum gravity research. They hint that space-time itself might be like a giant code. Geometry and locality could spring from the way quantum bits redundantly share information across space. Physical limits to computation. Nature sets strict caps on how fast and how much it can compute. The Bekenstein bound ties information to energy and size, and Landauer's principle links erasing a bit to heat and entropy. Put together, they suggest the universe is a finite, though stupendously large, computer. Emergent spacetime. Some theorists suspect spacetime is stitched from deeper patterns of quantum entanglement. In that picture, gravity and geometry are large-scale illusions woven by underlying informational links, making space a convenient byproduct of quantum data flow. Proposals beyond physics. These are speculative ideas that extend or challenge current physics by framing the universe more explicitly as a computational entity or process. Digital physics. Reality might be fundamentally discrete, a cosmic lattice of on-off bits evolving by set rules. Physical fields and smooth spacetime could emerge from this digital substructure, much like pixels form a picture. Proponents try to rebuild known laws from cellular automata or logic circuits, it from bit. John Wheeler's slogan says everything comes from an answer to a yes-no question. Observation asks the question, reality supplies the bit. In this participatory universe, acts of measurement don't just reveal facts, they help create them. Cellular automata universe. Conway's Game of Life shows that simple grid rules can spawn dazzling complexity. Imagine scaling that up. The universe as a vast cellular automaton where each cell updates by fixed laws, spawning physics as emergent behavior. Causal set theory. Replace smooth spacetime with a growing network of discrete events linked by cause and effect. Geometry then arises from this web of informational relations, potentially reconciling quantum mechanics with general relativity in an information-first framework. Quantum computational universe. Seth Lloyd argues the universe is literally a quantum computer. Every interaction is a quantum gate and the cosmic history is the output. He estimates the cosmos has performed roughly 10^120 operations on 1090 bits since the Big Bang. Second law of infodynamics. Melvin Vopson speculates that information entropy might decrease over time, making the universe a data compressor, not a disorder factory. If true, it would flip our usual reading of the arrow of time, just-in-time reality. Nicholas Giesen suggests the universe doesn't pre-compute every possible outcome. Instead, new information is rendered only when needed, much like a video game generating graphics as you move. The future is open, calculated moment by moment. Analogies and philosophical interpretations. These are conceptual tools and thought experiments that help explore the implications of a computational universe. They are not physical theories, but offer compelling ways to think about information and existence. Clockwork Universe, an Enlightenment-era picture of a perfectly predictable, machine-like cosmos. Quantum randomness has since complicated that view, but the metaphor still shapes how we picture deterministic systems and algorithmic processes. Simulation hypothesis. Nick Bostrom's argument: if future civilizations run many realistic simulations, the odds tilt toward us inhabiting one. Laws that look mathematical and tidy could simply be code. Detecting glitches, say subtle quantum anomalies, might one day test the idea. Kolmogorov complexity measures how short a computer program can be while still generating a given object. Low complexity means compressible. High complexity means irreducible randomness. The big question: could the universe itself be generated by a surprisingly short algorithm? Nature as algorithm. Think of the laws of physics as software incessantly crunching data. Evolution becomes a search algorithm, gravity an optimizing routine through space-time. This framing suggests math doesn't just describe reality, reality runs on it. Many of these ideas converge on a simple, radical question: is reality just information? The math of black holes, the logic of quantum theory, and even the architecture of space and time increasingly point to a universe that stores, transforms, and processes information and nothing more.